Okay, this is the pre-class lecture for October 10th. So now that we've learned how to determine RNS configurations for simple tetrahedra that are drawn like this, now there's a number of other variations on drawing chiral carbons that we need to try and determine RNS configurations for. And we'll start with, how do you determine RNS configurations of chair cyclohexanes? So first let's talk about how you would determine the configuration if you just had a, let's say I've got a chlorine here and a hydrogen here, and let's say I've got a bromine down here and I've got a methyl group here. And I call this carbon 1 and 2. So how would we determine the RNS configurations of carbon 1 and 2 in 1 bromo, 2 chloro, 1 methyl cyclohexane? And before we do that, remember that when we were talking about naming cyclohexanes, that we could not use the cis or trans terms when we had more than one or more than two substituents on a ring. And the reason is because cis or trans was specific in its relationship between just two groups. So when you have more than two groups, you have to use the R and the S terminology to write the name of this molecule. So this could actually, when we're all said and done here, this is going to be, right now it's a 1 bromo, 2 chloro, 1 methyl cyclohexane. And in front of this would be, in brackets, something, well, it'll be 1 something, 2 something, meaning it'll be 1 RRS or 2 RRS for the 1 bromo, 2 chloro, 1 methyl cyclohexane. So we have to determine the configurations of carbons 1 or 2 for this molecule. Now, the easiest way, I think, to look at cyclohexanes and determine RNS configurations is simply to isolate the carbon that you're going to look at. So let's say I'm going to look at carbon 2. What I'm going to do is I'm going to draw carbon 2 in exactly the same orientation that I had drawn it, that it was in the chair, or not in a chair, in the cyclohexane form. And then down here for carbon 1, I'm going to do the same thing. I'm going to draw it in exactly the same orientation. And so now what I can do is, if I can determine my 1, 2, 3, 4 Conangle Prelog sequence rules for this carbon, for carbon 2, I can then put the numbers here and then just simply manipulate them to get me the 4th priority group away from me if necessary. So if we look at this carbon right here, I've got a chlorine, a hydrogen, a CH2, and a C with a bromine and carbon on it. So the hydrogen is group number 4 and the chlorine is definitely going to be group number 1. Now over here I've got a CH2 group versus a carbon with a bromine and another carbon on it. So clearly this carbon down below gets priority group 2 and this is 3. So if I came up here, I'd say this is a carbon with, that's a carbon with 2 hydrogens and 1 carbon attached to it. Down here I would say this is a carbon with 2 carbons and a bromine attached to it, and so therefore the bromine wins priority over the carbon and hydrogen. So that would give me 1, 2, 3, and 4. Now one of the things you have to do before you start doing any group switching or rotating is take a second and see if the 4th priority group is away from you. Most of the time it won't, so you're going to have to do some sort of manipulation, but in this case it is. So we stop, we say, okay, the 4th priority group is now away from me. Going from 1 to 2 to 3 is now clockwise. So carbon 2 here has the R configuration, so it's going to be the 2R. Now let's look down here at carbon 1. Carbon 1 has a bromine, a carbon with CH3, a CH2, and another carbon. So I'm going to change colors here. Go to blue for this carbon. So we can agree that the bromine is going to be the first priority group. Then this carbon right here has 3 hydrogens attached to it. This CH2 over here has 2 hydrogens and a carbon. And this carbon up here that's attached to this carbon has a chlorine, a hydrogen, and another carbon attached to it. So in terms of the priorities, the carbon with 3 hydrogens is definitely going to be number 4. The CH2 that has 2 hydrogens and a carbon versus a chlorine hydrogen carbon, this is clearly number 2 because the chlorine wins priority, and then number 3. So by drawing the carbon out over here, I don't have to confuse myself with the cyclohexane ring. I can just simply isolate the carbon that I'm going to look at and then put the numbers in, and once I got the numbers in, then it's just simply a question of manipulating the tetrahedron. So the 4th priority group is away from me. I can either do group switching or rotation. If I was to do group switching, I would simply switch 1 and 4, and that's first switch, 2 and 3 the second switch, and so therefore going from 1 to 2 to 3 is clockwise. So it's 1R, 2R. So both of these chiral carbons have the R configuration. Now, if you didn't want to group switch, once you get the groups in, again, I'm just going to write out the original structure here. What I would do is I would hold 2 constant, and I would rotate 4 into 1, 1 into 3, and 3 into 4. That would give me a 4 here, then a 1 there, and a 3 there, again going from carbon 1 to 2 to 3. Now that the 4th priority group is away from me, it's still clockwise, so I still get the R. Okay. Now, another thing that you have to be aware of when you determine R and S configurations of cyclohexanes is the idea that, let's say I gave you, say I wrote the molecule this way. And I said, okay, what are the configurations of carbons 1 and 3 of 1-chloro-3-methyl cyclohexane, the way I've drawn it. Now, when you see this, what you have to do is you've got to put in the 4th groups for each of the chiral carbons. Remember, in a tetrahedral structure, you've got 2 bonds in the plane, a bold wedge, and so therefore the hydrogen that's attached here goes on the dashed wedge. Down here, where is the hydrogen? The hydrogen is going to be on the bold wedge because I've already shown the 2 bonds in the plane and the dashed wedge showing the CH3. Okay, so for this one, if you want, stop the tape, take a minute, try and determine the configurations of 1 and 3. Okay, if you did that, then let's see if you were right. If you didn't, then you'll see if I'm right. So let's take for carbon 1, let's write out the structure in that chiral carbon in exactly its same configuration. If I'm looking at this chlorine, I got chlorine, hydrogen, carbon versus carbon. Chlorine definitely group number 1, hydrogen group number 4. Now down here, what do I have? I've got a CH2 and I've got a CH2 here. So technically when I move from this carbon down to this one, CH2 versus CH2, those 2 are tied. So now let's continue on the ring. For the top group, I've got a CH2 versus a C with an H, a CH3. So this carbon now has a hydrogen and 2 C's attached to it. This carbon over here has 2 hydrogens and a C attached to it. So therefore the bottom group wins priority over the top group. So again, when these 2 CH2s are tied, we have to continue on down the ring until we find the point of difference. Okay, so now I've got for my top carbon here, for carbon 1, I've got my 4 groups. The 4th group is pointing away from me on the dashed wedge, so I don't have to do anything, but just simply go from 1 to 2 to 3. So the top carbon then is the R configuration. For carbon 3, let's draw its in its orientation over here. And so now I need to look, and hydrogen is always the 4th priority group, so it goes on the bold wedge. Now I'm going to switch back colors here. So looking at carbon 3, I've got looking here, I've got a CH2 versus another CH2, and so they're tied. So now I'm going to come up here to this CH2, which has 2 hydrogens and a carbon attached to it, versus the right-hand group has a carbon that has an H, a Cl, and a CH2. So this carbon has a Cl, an H, and a C attached to it. Therefore, the right side going through this CH2 and the next carbon gets the first priority. This side over here with the CH2 gets the second priority. And the CH3 has 3 hydrogens attached to it. Therefore, the CH3 is the 3rd priority group because it just has 3 hydrogens, versus the other CH2s having 1 carbon and 2 hydrogens attached to it. So now the 4th priority group's not away from me. If I wanted to switch groups here, I would simply switch 4 and 3 and 2 and 1. Now going from 1 to 2 to 3 is still clockwise. So in this case, both the 1 and the 3 carbons are R. So if I wrote the name of this molecule, it would be 1R, 3R, 1-chloro, 3-methyl, cyclohexane. That would be its name. Okay. Now I just realized that I'm doing cyclohexanes with more than one chiral carbon, but determining the configurations of chiral carbons, if you separate them, it just simply becomes determining the configuration of each individual chiral carbon separately. And this is the way I like to do it, is just simply to write the carbon in its orientation in exactly the same orientation, and then just work with the numbers as opposed to working with the groups. Okay, it's easier to rotate numbers than it is to rotate groups, particularly when some of those groups are part of cyclohexane rings. Okay, so that's how we can determine the configurations of cyclohexanes. Now, once you can determine the configuration of the chair or of these cyclohexanes when they have, let's say, bold and dashed wedges, the next thing we want to do is be able to write the configurations for the cyclohexanes when they're in their chair conformations. So in this case, I don't know how to name this molecule because I don't know how to name alcohols, but let's call this carbon 1 and this carbon 2. What are the configurations of carbon 1 and carbon 2? Well, what I need to do is I need to convert this chair cyclohexane structure into something like this with the normal cyclohexanes with the bold and dashed wedges, because I just showed you how to do R&S for those. So to convert a chair conformation into a cyclohexane with bold and dashed wedges, it's fairly straightforward. When I am looking at the left structure here, it's like I'm looking down on the ring and I'm seeing groups pointed towards me and groups pointed away from me, or groups above the plane of the ring and groups below the plane of the ring. So if I imagine myself up here looking down on this ring, I'm going to end up with a 1, 2 disubstituted ring. And now, for carbon 2 here, which group, the hydrogen or the chlorine, is pointing towards me if I'm above the ring? If you said hydrogen is pointed above and chlorine is below the plane of the ring, you're right. What about for the oxygen and the CH3? Again, if you're above the plane of the ring, is the OH above or below the plane of the ring? The OH is above the plane of the ring. So the OH goes on the bold dashed, and the CH3 goes on the dashed wedge. So once you convert a chair cyclohexane into this structure, then we can just use the rules or the procedures that we just used to determine R and S configurations of each one of those chiral carbons. Okay, if you want to test yourself, stop the tape here and determine the configuration for carbon 1 and carbon 2 of this cyclohexane. Okay, if you did that, let's see if you were right. So for carbon 2, I'm going to draw the exact orientation of the molecule. I've got hydrogen as always the 4th priority group. I've got chlorine versus carbon, chlorine wins. So now I've got a C with a C, an O, and another C, so a carbon with 2 C's and an O attached to it, versus up here I have a CH2, and this CH2 has 2 hydrogens and a carbon attached to it. So if I start with carbon 2, I'm looking at the lower group being the 2nd priority after chlorine, and then the CH2 group being the 3rd priority. So here is my, and I'm going to put a C in front of that just so we don't get confused with the numbers. So here's my ranking of the 4 groups. Now I have to move the 4th priority group to the back. If you want to group switch that, that's fine. How about I rotate it in this case just to sort of show you how that would be done. So if I make these rotations, I'm just going to write it a second time so that I don't get confused. My 4 goes back, my 1 comes forward, my 3 goes to the right, and then 2 never moved because that's what I grabbed to rotate around that carbon-carbon bond. Now with my 4th priority group away from me, going from 1 to 2 to 3 is counterclockwise, so C2 has the S configuration. Okay, let's do carbon 1. So for C1, I've got the carbon in this orientation. I've got oxygen versus carbon versus carbon versus carbon. Clearly the oxygen wins priority group 1. I'm going to switch colors for this carbon. So I've got a carbon with 3 hydrogens attached to it versus a carbon with a hydrogen, chlorine, and another carbon. And then for this carbon over here, I've got a CH2, so I've got over here, I've got a carbon with 2 H's and a C, the C being over here attached. So hydrogen, carbon, chlorine beats hydrogen and chlorine. So therefore the top group is group number 2. The group to the left is group number 3. And the CH3 with a carbon with 3 hydrogens, well, 3 hydrogens is lowest of either of those groups. They're number 4. Take a minute. 4th priority group is pointing away from me, therefore I can just go ahead and go from 1 to 2 to 3 automatically. That makes C2 the S configuration. So in this case, both of these carbons have the S configuration for that chair cyclohexane. Okay. What about that molecule? Let's call this carbon 1 and carbon 3. Can you write the configurations for carbon 1 and carbon 3 of this chair cyclohexane? Again, stop the tape, try it. Well, let's see if you're right or not. Okay, so first thing we've got to do is we've got to convert this to our chair. We're going to convert the chair to the regular one. So I'm going to call this carbon 1 and this carbon 3. Again, being above the plane of the ring, looking down, I see an OH group above the plane of the ring and a Cl below. I see an ethyl group above the plane of the ring and a Br below. Okay. So now looking at carbon 1, I've got chlorine versus oxygen versus carbon versus carbon. Chlorine wins 1, the oxygen of the OH wins 2. I've got a CH2 versus another CH2, so we move on. Then I've got a CH2 versus this carbon down here that's got the bromine and the ethyl group attached. So the bottom group clearly wins priority group 2, or I'm sorry, 3, because we're up to 3. And then the lowest priority group is the one to the left. So there's my 1, 2, 3, and 4. Orient the 4th priority group away from you. So I'm going to switch 2 groups twice. Going from 1 to 2 to 3 is counterclockwise. So carbon 1 has the way I've numbered them, has the S configuration. What about carbon 3? Bromine versus carbon versus carbon versus carbon. Bromine clearly wins 1. This carbon is a CH2. This carbon's a CH2 to the left, and then the one on the bold wedge is a CH2. So now I'm tied. So now I need to move to the next one. The next carbon up here has 2 hydrogens and a carbon. The carbon here has a Cl, an O, and another C, versus now this CH3, which has 3 hydrogens. So looking at these 3 groups then, because I was tied with the initial CH2, that CH2, and that one. Now continuing on, the chlorine, oxygen, carbon wins the second priority for the group on the right. This 2 hydrogens and a carbon wins for the one on the left. And then the CH2, CH3 with the CH3 just having 3 hydrogens, it's priority group 4. Switching my groups. Going from 1 to 2 to 3 is clockwise, and so therefore the carbon 3 has the R configuration. Okay. Okay, so that's how we look at chair cyclohexane conformations. We convert the chair into the cyclohexane where I'm looking down the ring, and then isolate each chiral carbon, determine the determine the rankings from 1 to 4, and then just simply deal with each carbon individually as if it was a single chiral carbon by either group switching or doing rotations. Okay, another thing that we have to do is determine the conformations of molecules using Newman projections. Okay, the next topic that we have to look at is how to determine configurations of chiral carbons when they're in Newman projections. And usually when they're in Newman projections, we have to convert them into another structure that allows us to determine whether we have into a tetrahedral form where we've got bold and dashed wedges. Before we do that, let's look at some models here and try and convert the pictures of the molecules here in the model into what we would see if we were to write tetrahedral representations of each of these two chiral carbons. And so if you looked at this molecule over here on the right, what I essentially have is I have a carbon-carbon bond that's in the plane of the screen. For this red group, which I'll just go ahead and call R, and this green group down here, those are also in the plane of the screen, and so I would give those regular bonds. Now the blue is pointing towards you, or is pointing towards the front of the screen, and so that blue ball would be in front, and so would this orange ball down here would also be pointing towards you, and they both would then get bold wedges. There's a purple group here in the back, which would get a dashed wedge for the purple, and then the white group in the back would also be on a dashed wedge. So this is what's typically called a sawhorse representation of an alkane. And this would actually correspond to if we went back and thought about staggered and eclipsed conformations. If you look down this carbon-carbon bond, which one would it be? If you said eclipsed, you're wrong. It's staggered. And we'll come back, we'll do that in the next slide. We'll convert this structure into the Newman projection. But if you look down here, because these two groups are in the plane, the red and the green, this would actually be the staggered conformation. Now, if I moved it into the eclipse by rotating this hydrogen up in the plane, or moving this blue group up into the plane, then I would get this structure, and now this structure is the eclipsed conformation. And so it would look like this. I did nothing to the carbon on the left, so my red is in the plane, my purple group is behind, and my orange group is ahead, or pointing towards you. Now all I did was move the blue in the plane, so now the blue and the red are eclipsing each other. Then the white is down here behind you, and the green is on a bold wedge pointing towards you. So we can manipulate these structures simply by rotating, but we have to have a general idea when I look at this saying, okay, this is basically the eclipsed conformation. And so the red and the blue are eclipsing each other. They're in the same plane. Actually, the purple and white groups are in the same plane, and orange and green. Orange and green are pointing towards us. Purple and white are pointing away from us. So if we can manipulate the molecules into this type of a structure, then what I can just do is simply separate the two carbons, determine R and S configurations by simply ranking the groups and then putting the fourth priority group away from me. But this is how we would write these structures, and these are the models that they correspond to. Now, converting this sawhorse representation into a Newman projection and vice versa is how we would get the configuration of a Newman projection. So let's say that I have this structure, which was my first one that I wrote earlier. I had the red and the blue, well actually, and the green down here in the plane. The blue was on a bold wedge pointing towards me. The white was pointing away from me. The orange group was pointing towards me on a bold wedge, and the purple was pointing away from me on a dashed wedge. So if I look at this, this is my structure. Now imagine myself over here looking at this, going to draw the Newman projection of this molecule. Well, if I drew the Newman projection of this, I would simply come down here and say, okay, Here's my Newman projection the way I've written it. It's in the staggered conformation. So pointing towards me on now the left carbon, the carbon on the left becomes the front carbon, and the back and the right carbon now becomes the back carbon. Of course, if you want to completely reverse that, you'd look at this molecule from the right-hand side, but I'm going to look at it from the left-hand side. So the left is the front carbon, so what do I have? I've got the red group in the front, the purple to the left, the orange to the right, and in the back the green is anti to the red group, the white group is over here to the left, and the blue group is to the right. So converting from this structure into this Newman projection just simply requires me to look over here and convert the structure. But these two bonds right here are the key because they tell me the two groups are then going to be basically anti to each other in the same plane. Okay. Now converting backwards from this structure into this to determine R and S configurations is then going to require us simply to put the structure into this staggered conformation and then completely reverse it. Or we could also convert this into the eclipsed conformation and look at it as a Fischer projection. But we'll do this. We'll start with this to begin with because this is sort of the way the book does it. Okay, so let's try a practice problem here. Let me draw a staggered Newman projection. I'm going to put a hydrogen here, a bromine here, a CH group, CH3 group there, an OH here, a Cl, and how about another CH3 group here? And the question is, what is the configuration of the front carbon? What is the configuration of the back carbon? Are they R or are they S? Now, if you're an overly ambitious student at this point, stop the tape and see if you can work this out. If you're not, well, then here's how we would do it. Okay. So what I'm going to do is I'm going to convert this into that structure. And remember the front carbon, so what I'm going to do is I'm looking at it this way. What I'm going to do is I'm imagining now I'm over here looking at this, looking at that Newman projection down the carbon-carbon bond, and the right structure is what I'm going to see. So my H and my CH3 are anti to each other. And then the front carbon, remember, is the left carbon. So the bromine, when I look at it from this perspective, or when I rotate this molecule around, the bromine then would have gone to the back, and the methyl group is pointing towards me. So again, if I'm over here, the methyls are towards me, the chlorine and the bromine are away from me, and the hydrogen and the CH3 are in the same plane as the CC bond. So the methyl is pointing towards me. How about when I look at this look at the back carbon then from this perspective? Well, the OH and the CH3 are pointing towards me, or no, they're not actually. That's the OH that's pointing towards me. So the OH would go on the bold, and then the chlorine is pointing away from me. And the CH3 then, this CH3 down here is in the plane. So I'm converting from this Newman projection into this one. Well, then what I can do is I can simply separate these two in half, and let's say I look at the left carbon, and then I'm going to look at the right carbon, and I'm going to determine R and S configurations. So now let's put my numbers in. Definitely hydrogen is 4 and bromine is 1. I've got a CH3 group versus a C that's got more than hydrogens attached to it. This is a chlorine, oxygen, carbon versus a carbon with 3 hydrogens. That group is number 2. This whole group over here is number 2 versus the CH3, which is group 3. Now let's go to this carbon on the right-hand side. What do I have? I've got a Cl, an OH, a CH3, and then on the left-hand side, the carbon with the bromine, hydrogen, etc. So I've got chlorine, oxygen, carbon versus carbon. So chlorine wins 1, the oxygen wins 2. Here I've got a carbon with 3 hydrogens attached to it. Over here I've got a carbon with a hydrogen, a bromine, and another carbon. That wins. And so this is number 3, and the CH3 group is number 4. So I've split these 2 chiral carbons in half. Remember, the left carbon was the front carbon, the right carbon was the back carbon, and so now we can just go ahead and determine their configurations individually. So 4th priority group's not pointing away from me. I'll go ahead and switch 1 and 4 and 2 and 3, and now I'll get going from groups 1 to 2 to 3 is now counterclockwise. So the left carbon that was the front carbon is S in its configuration. Over here, the 4th priority group is not away from me. So I'll switch 1 and 4. I'll switch 2 and 3. Now going from 1 to 2 to 3 is clockwise. So the right carbon, which was the back carbon in this, is now R. So the front carbon had the S configuration. The back carbon had the R configuration. Okay, so when we're given a Newman projection like this, we can go ahead and just simply convert it to this sawhorse representation, split the 2 carbons in half, determine left, which was front, and then right half, which was the back. Okay, this blank slide means that it's time for you to try a problem. And let's make it more difficult. How about we put this in the eclipse conformation to begin with. So I'll put a Cl here. How about I put an H there? How about I put an OH on the front carbon, and then I put a CH3 here, maybe a Br there, and an H there. So can you determine what the configuration of the front carbon is and what the configuration of the back carbon is for this Newman projection? Want to stop the tape, try it, and then come back and see if you were right. Now, if we're going to do this molecule this way, a couple of ways I can do it. First, if it's in the eclipsed Newman projection, that eclipsed Newman projection look like this. Right? The Cl and the CH3 are both up. So again, my perspective is over here. So I'm looking down that carbon-carbon bond, and I'm saying, well, the chlorine is the left, that's the front carbon, and the CH3 is on the right carbon, which was the back carbon. And they are now in the same plane. If I'm looking at the left carbon, or what was the front carbon, the hydrogen is pointing towards me. If I'm looking at the back carbon, which is the bromine, it's pointing towards me. For the front carbon, it's the OH that's pointing away, and the hydrogen over here is pointing away. So all I did was take this Newman projection and realize that in the eclipsed conformation, we have the 2 groups that are both here pointing upwards. They're in the same plane, and so now I've written the sawhorse in this representation. Okay, if you don't like that, if you wanted to, what you could have said as an alternative is you could have said, you know what, I want to put it in a staggered conformation, and if you would have put it in the staggered conformation, you would have gone like this. I would have said, okay, well, let's just move this chlorine or this methyl group over here, then the hydrogen up 60 degrees to put it there, and then the bromine over here 60 degrees there. Now I've got my molecule in my staggered conformation. As I just did the last problem, that means that its sawhorse representation would look like this. I have my chlorine and my bromine in the plane. Again, my perspective is I'm over here looking at the molecule that way. And so my chlorine is on the left, bromine is on the right. The hydrogen is pointing towards me. The methyl group is pointing towards me. The OH on the left carbon, which was the front carbon, is here. The H over there is pointing away from me. And notice, to get from here to get from the top structure here down to the bottom structure here, all I did was rotate 60 degrees and move the methyl group towards me. Either way you do this, now let's split the carbons in half, or split the chiral molecule in half. So now I'm going to have, here's my left carbon, here's my right carbon, drawn in exactly the same orientation. I've got a chlorine, oxygen, hydrogen, and carbon. Well, that's really easy. Chlorine number 1, oxygen number 2, carbon number 3, and hydrogen number 4. Remember, there's a carbon over here, so when I do this carbon on the left, I'm treating this whole group as a CH-Br-CH3 group. So carbon, chlorine, oxygen, hydrogen. So there's my numbers. For the right carbon, I've got hydrogen, bromine, carbon, another carbon. Hydrogen definitely 4, bromine definitely 1. I got a CH3 group here versus a carbon with, again, more than 3 hydrogens. Group number 2, group number 3. Okay. So looking at the left carbon, I'm going to switch carbons 2 and 4. Going from 1 to 2 to 3 now is clockwise, so that's the R configuration, which means that the front carbon had the R configuration. For the right-hand carbon, which was the back carbon, 4 is already pointing away from me, so going from 1 to 2 to 3 is clockwise, so it's the R configuration. So I get R and R. If we did this down here with a staggered conformation, I would see hydrogen, chlorine, oxygen versus carbon on the right side. That's number 1, number 2, number 3, and number 4. I would switch 4 and 2, and then 3 and 1. My 2 group switches makes the configuration the same as it originally was. Going from 1 to 2 to 3 is still R. Good, I get the same answer either way, which I should. Hydrogen, bromine, carbon, carbon. Bromine number 1, hydrogen number 4, CH3. Number 3, carbon with more than 3 hydrogens is number 2. Fourth priority group still away from me, still the R configuration. Okay, so that's how we convert the Newman projection into the sawhorse, and then once we have it in the sawhorse, we can split the 2 chiral carbons up and determine the configuration of each one of those. Okay, now there's another way to represent a chiral carbon which is done quite a lot, and that's using what's called Fischer projections. Here's a model showing our normal tetrahedral representation of a carbon atom. The blue and the red bonds are in the plane of the screen. The green is pointing away from you, so we would put this on a dashed wedge. And the white is pointing towards you, so that goes on a bold wedge. Now, oftentimes, we write a single chiral carbon in what's called a Fischer projection. The Fischer projection is a model like this. I've taken this model and I've rotated it so that the 2 the red and the white are now bold wedges pointing towards me. Let me make this a little bit. Let me make these two a little bit better. There. And the blue and the green are actually pointing away from me. Why did I write H? So in this Fischer projection, none of those bonds are in the plane of the screen. You've got two pointing towards you and two pointing away from you. Now, typically what's done with the Fischer projection is it's written like this. And so this shorthand notation then translates to this sort of bold dashed wedge structure. So when you see a structure like this, this is in the Fischer projection. And so what we have to do is we then have to convert the Fischer projection into the bold and the dashed wedge orientation. Okay. And so in a Fischer projection then, this is sometimes called the bow tie structure. And even your book uses this analogy. It's the bow tie structure because we have the person wearing the bow tie. So doing or determining R&S configurations of Fischer projections, if you're doing the group switching method, is actually pretty straightforward, because our group switching method just simply means that we move the lowest priority group to a bold wedge. Does it matter whether it's the top or the bottom bold wedge? No, it doesn't. Now, if you're going to rotate groups, you have to be careful, because there's something that the book and people will tell you about Fischer projections that you never ever do. I'm not going to tell you what you shouldn't do. You can read that in the textbook, but if you can imagine if my white group here, and this is normally a hydrogen, if this was pointing towards me and I wanted to put it on either the blue or the green positions pointing away from me, what I'd have to do is I'd have to come over here with my hand and grab the red and then rotate the hydrogen back, the blue group here and the white group there, so that I'd have to rotate around those three groups to then put the white back on a bold wedge or on a dashed wedge in order to determine then the R and the S configuration of, or the configuration of, that chiral carbon. So if you're going to rotate, you have to be careful, because you have to hold either of the two blue ones constant, or either one of the groups on the bold wedge constant. So you have to grab one of them. Down here in my model, that's what I do here, is grab the red, and then you'd move the white back, the blue to the green position, and then the green position over there. Sort of, again, like you're rotating half of a Newman projection. Okay, so that's how you can rotate, or you can group switch, either one. So let's say that I gave you a Fischer projection, and I put a hydrogen here, a bromine here, a CH3 here, and let's make it a little more complicated. Let's put a CH2, another CH2, and an OH over here. So first thing is you got to assign priorities on these groups. So it's bromine versus carbon versus carbon versus hydrogen. Hydrogen clearly number 4, bromine clearly number 1. Looking at these two carbons, what's attached to this carbon? 3 hydrogens. What's attached to this carbon? 2 H's and a C. Okay, which one wins? the two H's and a C, so that becomes group 3. This becomes group 4. Now let's translate that into the bow tie structure. So I've got 1, 4, wait, sorry, this one was, what am I thinking? This is 2 and this is 3. There. So then this is group 3 and that's group 2. Stop, fourth priority group is pointing away from me. Therefore, going from 1 to 2 to 3 is counterclockwise. So this has the S configuration. And actually, Fischer projections are pretty straightforward because you got a 50% chance of having the fourth priority group on a dashed wedge. If not, just group switch or do your rotation, being careful, and put the fourth priority group away from you, and then you can go ahead and determine R and S configuration. Let's make it a little more difficult. Can you determine the R and S configuration for this structure? Okay, if you want to stop the tape, try it, see if you were right. I mean, you got a 50-50 chance of getting it right. It's either R or S. Now, I got carbon versus carbon versus carbon versus chlorine. Chlorine number 1. For the carbon, what's attached to this carbon? Well, you got to go back to the last lecture and remember that the equivalent structure here is going to be this, so that carbon has 2 O's and an H attached to it. What's attached to this carbon over here? 2 H's and an I. What's attached to this carbon down here? 2 H's and an O. Which one wins the highest priority? Iodine beats hydrogen, oxygen. So this is group number 2. Now between 2 oxygens and a hydrogen versus 2 hydrogens and an oxygen, 2 oxygens and a hydrogen wins priority group number 3. CH2OH with 2 hydrogens and an oxygen wins number 4. So if I come over here and I clean it up and I draw my bow tie structure, the numbers are 1, 3, 2, and 4. 4 is pointing away from me, going from 1 to 2 to 3. Didn't have to switch any groups because the fourth group was away from me. Going from 1 to 2 to 3 is counterclockwise. And so this is the S configuration. Okay. So once you determine your R and S, dealing with Fischer projections is pretty straightforward. Okay, now what we do with Fischer projections is we oftentimes put multiple chiral carbons in the Fischer projections. And so here's a model showing you 2 chiral carbons in a Fischer projection. Now you may say, hey, I think I've seen that model before. And if we go back here, you have. That model is this one, only now what I've done is now I've twisted it 90 degrees and I'm looking at that model on its side. So now if I write this in a Fischer projection, I can actually draw the Fischer projection like this. And in this case, it's really kind of half a Fischer projection because this bond between the 2 carbons here, between the top and bottom carbons, is in the plane. So really when I'm writing the Fischer projection like that, I'm kind of writing it like this. That's actually what a Fischer projection with multiple chiral carbons looks like. So, or actually I shouldn't say multiple chiral carbons, I should just say 2 chiral carbons. So when I have this molecule, here's my structure. So looking at the top carbon here, the red group is on the right, the orange group is to the left, and the purple group is pointing behind me, right? So this is what I'm seeing. Red, orange, purple. For the bottom carbon, I see blue and green, and I can't see the white because it's behind me, but it's there. Okay. And so dealing with the Fischer projection, first of all, when you look at this Fischer projection, what is the confirmation, or what is the structure of this in terms of looking at it as a Newman projection? If I'm up here looking down on that carbon-carbon bond, is it staggered or eclipsed? If you said eclipsed, you're right. So when a Fischer projection is drawn like this, it's written in its eclipsed conformation. So in a way, all this is just simply the structure that we looked at earlier. Remember, we looked at this? This structure is that same structure, only, I don't know, imagine looking at it from underneath so that those two bonds are actually pointing away from you. So the purple and the white groups would be on these two positions, respectively. So we've already kind of seen how to do a Fischer projection of two carbons. Simply, all you do is you've got it, convert it to your bow tie structure, divide the molecule in half, determine the configuration of the top carbon, then determine the configuration of the bottom carbon. And here, if you do this, you basically just want to put your low priority group on, you want to put your lowest priority group on probably the bold or on the dashed wedge position, which are going to be this one and this one. You still could put it here, and that will give you the correct answer for most problems. This means another problem. Can you determine the configurations of the top and the bottom chiral carbons? Can you stop the tape and figure that out? Okay. If you did, let's see if you're correct. So let's separate here the top carbon from the bottom carbon. I look at the top chiral carbon. What do I have attached? Hydrogen, chlorine, oxygen, carbon. 4, 1, 2, 3. Don't even have to go any further. The atoms directly attached are carbon, oxygen, chlorine, hydrogen. I can set the 4 groups that way. For the top carbon, is the 4th priority group pointing away from me? It is not. I'll switch groups 2 and 3 and 1 and 4. 4th group is now pointing away from me. Going from carbon 1 to 2 to 3 is counterclockwise. Top carbon has the S configuration. How about the bottom carbon? Well, I've got bromine, oxygen, carbon, and carbon. Bromine number 1, oxygen number 2. So how about these two carbons? This carbon over here has 3 hydrogens attached to it. What does this carbon have attached to it? An H, an O, and a Cl. So 3 hydrogens versus something with 2 that are better than a hydrogen. This is group 4. This is group 3. 4th priority group pointing away from me? Nope. So I'm going to have to switch my 2 sets of groups. going from 1 to 2 to 3, now that the fourth priority group is away from me, is now counterclockwise. That is the S configuration. Okay, so that's how we handle multiple chiral carbons that are in Fischer projections. Sort of like we did before, except now they're in the bow tie structures. Now, I want to introduce a new stereochemical term, and then that's the end of the lecture for today. This is a little bit to digest. Let's say I'm going to go back here, and I'm going to start with this molecule since I already determined the S, that these are both SS. So let me write this structure out with the H, the Cl, and the OH. H, Cl, and OH. Oops. And CH3, OH, and Br. CH3, OH, Br. Now, I just determined that those two carbons those two chiral carbons have the S configuration. So, for the sake of argument, I'm going to call this structure A, and I'm going to say that this has the, how would I number this? This would get, let's call this, let's not even screw around. This is carbon 1, this is carbon 2, top and bottom. So I'll call this the 1s, 2s. Okay, those are the configurations of those two chiral carbons. So, if I have these two chiral carbons, what would the enantiomer of this molecule look like? Now, we haven't drawn an enantiomer of a carbon with more than one chiral center in it. But we do know that enantiomer means non-superimposable, non-mirror image. Non-superimposable mirror image isomer are enantiomers. So let's draw my Fischer projection. I'm going to draw it in the bow tie structure. Let's draw the mirror image of A, and we'll call that B. So if I look at the top carbon, my OH is going to be here, my H is going to be here, and my Cl is going to be there. Right? I've written the mirror image of the top carbon. Now write the mirror image of the bottom carbon. If you want, stop the tape, write it. If you did that, there it is. So B is now the mirror image of A. So these two are enantiomers of each other. What are the configurations of carbon 1 and carbon 2? So this should be the 1 blank 2 blank isomer. Well, for the top carbon, if its configuration is S, what's its mirror image's configuration going to be? If you said R, you're right. How about carbon 2? What's its configuration going to be in molecule B? It's going to be R as well. So look at this. The enantiomers of this molecule, of the 1s, 2s, is 1r, 2r. When I write the mirror image isomer, I have inverted, and that's the term we use, each of the chiral centers so that now what was R became S and vice versa. So A and B are enantiomers. Let me write another structure. How about I write the configuration? I'll put the top carbon in the S configuration like it was over here in A, but I'll put the bottom carbon in the R configuration. So now I'm going to write the 1s 2r configuration. That now is going to give me a new molecule C. Now, is C superimposable on either A or B? The answer is no, right? One chiral carbon has the same configuration, but the other one has the opposite. So there's no way I can superimpose C on B or A. But they're not mirror image isomers. So the relationship then between B and C is that they are non-superimposable, non-mirror image isomers. And so now what we need is we need a new stereochemical term to talk about molecules that have more than one chiral center and are non-superimposable, non-mirror image isomers. Because so far we've just been dealing with molecules with a single chiral center, and a molecule with a single chiral center, it's either R or S, and so they have to be by definition either the same or mirror images. But here's a new relationship. Non-superimposable, non-mirror image isomers. Molecules where one chiral center, let's try this one, where one chiral center has the same configuration and, again, I'm comparing over here, the other chiral carbon has the opposite configuration. If I looked at B here, B would have the two carbon with the same configuration and the one having the other one. I guess I should have done this. This is actually my relationship here wasn't between A and B, or between B and C, it was between A and C. But this relationship also holds between B and C. So the relationship between A and C and B and C are that they are non-superimposable mirror image isomers. What do we call those? We call those diastereomers. So diastereomers are non-superimposable, non-mirror image isomers. They are molecules where at least one chiral carbon, and I'll provide you an alternative definition, at least one chiral carbon is or has the same configuration and at least one chiral carbon has the opposite configuration. And the reason I say at least one is because this definition will cover more than one chiral center. So if you had 5 chiral centers and 4 of them were the same but one was different, those would be diastereomers. Okay. So diastereomer is a new type of relationship. Now, is there a fourth molecule that I can draw in this set that is also a diastereomer to A and B? Well, yes, I can draw molecule D, and D would be the mirror image of C. So if I draw the mirror image isomer of C, it would look like this. And what would its configurations be? The top carbon has the R configuration now, and the bottom carbon has the same configuration as it did in A, so this is now the 1R2S. So D and B are diastereomers. D and A are diastereomers. What's the relationship between C and D? They're mirror image isomers, so they are enantiomers. Okay. So one of the things that is fundamental about chirality is that every chiral carbon can either have the S or R configuration. And so when you end up having pairs of molecules that are either enantiomers or diastereomers, the first thing that we should note is that for each molecule, it has one and only one mirror image. And those are enantiomers. That's its enantiomer. But it can have many non-superimposable, non-mirror image isomers, the so-called diastereomers. So we have two chiral centers in this molecule. And we have four possible stereoisomers from those two chiral centers. When we had one chiral center, how many stereoisomers did we have? 2. So in general, you have 2 to the n number of possible stereoisomers, where n equals the number of chiral carbons. And of those, there are pairs of enantiomers, and then the rest of the relationships are diastereomeric. Okay. So that's our new term. Are molecules diastereomers? Are they enantiomers? Okay. So, what about the differences in diastereomers? What are their physical and also then their chemical properties? Do they have the same chemical and physical properties? Do they have different chemical and physical properties? Remember, for enantiomers, what physical property is different for enantiomers? Optical activity, the way they interact with plane polarized light. What physical properties are what physical properties are different for enantiomers? Rotation of plane polarized light. Everything else was the same. What chemical properties are different for enantiomers? When they react with other chiral molecules, with other enantiomers. If they react with a non-chiral molecule, they react the same. So what are the chemical and physical property difference of diastereomers? Well, this is easy. The diastereomers are basically different molecules. And therefore, they have different chemical and physical properties. So if you have two molecules that are diastereomers, they have different boiling points, different melting points. If you put a pair of diastereomers onto a TLC plate and you have the appropriate conditions, they will separate out into two spots. If you injected them into the GC, again, with the best conditions, they will separate into two peaks. Diastereomers are different molecules. So if I had a mixture of A and C, they'd have different melting points. Now sometimes diastereomers have very similar melting points, but they by definition have different ones. It's not like an enantiomer where the melting points are exactly the same. And here's an example of that. Here are two drug molecules that are diastereomers of each other. One is ephedrine and the other is pseudoephedrine. And what you can see in these diagrams is that carbon 1 here in ephedrine and pseudoephedrine, carbon 1 has the opposite configuration, but carbon 2 has the same configuration. And so that makes this pair a diastereomeric pair. They have different physical reactions in the body. Pseudoephedrine, which actually has a second hydrogen added to it. We add actually HCl to this molecule and make what's called pseudoephedrine hydrochloride. That's Sudafed. That's what you have to go when you have to go to the drugstore to purchase it now, thanks to the Methamphetamine Control Act of 2000 and I think 4 or 5. You have to show your driver's license, and you can only buy up to like 3 grams of pseudoephedrine a day because it's used to make methamphetamine illegally. So pseudoephedrine hydrochloride is the drug Sudafed. It we take for stuffed up noses. It's an antihistamine. Ephedrine, which is also when it was sold sold as the hydrochloride salt, where basically you had an N plus and a Cl minus species. Ephedrine was in over-the-counter diet drugs that helped you lose weight, because ephedrine is in essence, it speeds up your metabolism. They've banned it in all weight loss products as of a few years ago. But they do different things in biological systems. They're different molecules. They actually have different melting points. Ephedrine melts between 37 and 39 degrees. Pseudoephedrine melts between 118 and 120. So they have different diastereomers have different physical properties and different chemical reactions. Unlike enantiomers, which have exactly the same reactions with non-chiral molecules and have exactly the same physical properties except for how they rotate plane polarized light. Diastereomers will still rotate plane polarized light. And if you had one enantiomer of pseudoephedrine would be the D form, and the other enantiomer would be the L form. And one enantiomer of ephedrine would be the D form, and the other version would be the N form or L form. Okay, so diastereomers they're different molecules, but diastereomers still have enantiomers of each other. Okay, so you should be able to determine RNS configurations of Fischer projections from sawhorses and Newman projections, from cyclohexane and chair cyclohexane representations. And then I've introduced this idea of a new type of stereoisomer where a pair has at least one chiral center the same and at least one chiral center of opposite configuration. Okay. So your online quiz will probably ask you to determine RNS of all 3 of the examples that I gave you, and we will deal more with the diastereomers and introduce a new and final stereochemical term called mesocompounds, but we'll do that after Friday's one-day fall break.